Hello everyone. So let us get started with today's tutorial. So in this tutorial, this is the tutorial number 3. So we will be first going through what has been taught in the previous lectures, and then I will try to solve a problem online and and address if any questions are there from previous lectures or from the current tutorial. Okay, so let's get started. So first we will get familiarized with and again revisit the concept of conversion of a differential form of an governing equation to an algebraic form, right? So when we saw that the governing equations are of form of PDEs, right? PDEs, I mean partial differential equation, and we had developed and sir has already taught you how to develop a um, scalar transport equation, general scalar transport equation phi. Okay, so then we will go from the differential form to an algebraic form, and then we'll see that what are the different methods by which we can solve this algebraic form to get the solution that we need. Then finally, we'll do a example problem to get a better understanding of the solution methods and um, how we will go about solving the things, solving the governing equations and the phenomena that we want to simulate in CFD. Okay, so let's start by the general scalar transport equation. The temporal term. Okay, let's write it in the vector form. Del dot rho u vector phi, the convection term, del dot gamma times gradient of phi, which is the diffusion term, and at last the source term. Okay, so we will first take a small problem, not small problem, but a simpler problem to deal with. We will eliminate few terms. For example, we will study the steady diffusion equation with source term. So then we can neglect this term, this will go to 0, 0, and only this term will survive. Okay. So it goes something like this. Now, if you remember from our previous discussions, somebody wanted to join us. Okay. So if you have gone through the lectures, so there are two methods, right? So two methods were introduced: the finite volume method and the finite difference method. Okay, and we saw that the finite volume method has the conservativeness built in in the formulation, while the finite difference method, we saw that it's not conservativeness is not maintained in each and every cells, but overall in the whole domain the conservativeness is maintained. Okay, so but in our from now on we will only be concentrated in the finite volume method. Okay, how we will solve different problems using finite volume methods. Okay, So if you remember from the finite volume method, what we had to do is that first we had to uh, integrate the governing equation in the control volume. Then we invoke the Gauss divergence theorem. What does it do? It converts a control volume integral to a control surface integral, right? Then we will form a algebraic form of the governing equation. Okay, so let's get started. Right. Think. Okay, so what was our equation? The steady diffusion equation. It was del dot, sorry, del dot gamma times gradient of phi plus s phi equal to 0. Now we assume a 1D problem. So this will become what? So this del operator will become del dou by dou x. Okay, since it is a 1D problem and there is no time derivative, we can simply write it as a ordinary differential form, gamma times e by dx plus s phi. Okay. Now we will take the volume integral. Okay, we can write this term okay, I think, yeah. So what about this term? We'll write it in a different way to make use of the Gauss divergence theorem. We can use it in this way also, but I'll just write it in a different way. Del dot dx and dv. Okay, and what does the Gauss divergence tell us? Tells us that the divergence of any vector field, we can convert this volume integral to a surface control surface integral by just removing the divergence operator and the replacing the control volume integral to a surface integral by dA vector. Okay, and this dA vector is nothing but the dA magnitude, the magnitude of the area times the normal vector. For example, if this is the area and it is say a meter square and this is the normal, so this will be a n cap, right? This dA vector will be a n cap. Okay, so now what does this mean? So this divergence operator we can just get rid of it and we can convert this control volume to a control surface integral, and this will be nothing but I cap times dA vector. So why did I write I cap? Okay, let me just give you a visual uh, context of how this came out. So we are taking a 1D domain, right? And say this is point P, this is point west, this is point east, okay? And this is the positive x direction. And we are taking a 1D problem, right? So since we are taking a 1D problem, what we can do is that uh, the del operator, the del vector or the del operator will be nothing but dou by dou x I cap plus everything else will be 0, right? So it will only get multiplied with dou by dou x of I cap. Okay. And this is the gradient. So if you remember, the formula was del dot gamma times gradient of phi, okay? And this we have done with the divergence operator, so we are only left with the gamma del phi, which is nothing but gamma times dou by dou x I cap plus everything is 0 times phi, right? So thus we have the term dou phi dou x I cap, okay? I hope there is no confusion here. Now looking at the domain, we see that we have two control surfaces, right? So this is the one control surface. Let us term it as small w and small e, the east face and the west face. And we'll assume that the area vector, the magnitude of the area is 1 meter square. Okay. So what will be the area vector? So this is nothing but a surface integral, right? So this integral is something like this. And this integral we can again break it down into a summation, right? Because integration is nothing but a sum over the whole thing, right? So for example, in this case, since it is a 1D case, we'll only have two surfaces. So this integral will just become the summation of flux at the two two boundaries, right? And what will be the area vector? So, so if you notice here carefully, this is the pth point we are interested in, and this is the W boundary, this is the E boundary, and we know that the area magnitude is 1. And what will be the vector? So vector of this area will point outwards, that is nothing but I cap, and the area vector and the area normal of this west face will point to the minus I cap direction, because this is the x direction here. So whatever will point away from the x direction, it will be negative I and it will be positive I, okay? So this will translate to a summation of faces phi dx of some face and dA vector of some face, okay? So in our particular case, there are two faces only, right? So this will be phi dx at east face times I cap times dA vector of east face plus gamma dp dx of west face I cap times dA vector of west face. Plus again we have this control volume integral of S phi dV. Okay. So this much is clear. Now how to deal with it? So we have a cell, right? We are computing the all the quantities, the phi p in this cell, and we will take a assumption that the thing is the source term is uniform throughout the control volume, and we will denote it as s phi bar. Okay, this is the average s phi value throughout the domain. And then we can, what can we do? If we assume this, we can replace this integral into s phi bar times the volume, the delta v, which is nothing but delta x for a 1D case. Delta x times a dA, the area times delta x, which is nothing but 1 times delta x is equal to delta x. Okay, so this becomes s phi bar times delta x. Okay, okay, let's go to the next page. Okay, so we had this form d phi dx I cap at east face dA vector at east face plus gamma d phi dx I cap west face dA vector at west face plus s phi average times delta x equal to 0, right? And this is our domain. Yeah, and this is our domain. So this is P, this is, okay, sorry, this is west, this is east, and this is delta x, which is the volume, and this is the area. The area magnitude is 1. Okay, this is small w boundary and small e boundary. Okay, now we have reached this part. So let's see what the dA vector E looks like. So this is this face, right? And here the normal is pointing at the positive x direction, right? This is the x direction, and the area is 1. So this is nothing but I cap, and the W vector will be nothing but minus I cap. Okay. So now, so this I cap will get multiplied with I cap and will become 1. So this becomes d phi dx at E. Okay, because I becomes 1, and minus I and I will get multiplied and become minus 1. So this is become minus gamma d phi dx at W. Okay, plus s phi bar times delta x equal to 0. Okay, now we have most of the things ready. Now what we'll need to model this part, right? So we'll need a profile assumption. What do we mean by a profile assumption? So in real life, the signals, for example, phi in space might vary like this, right? This is a continuous function, and it is varying like this. And to accurately model this, we'll need a lot of points, right? A lot of points to accurately model this, or else we'll not be able to capture every single detail of this function, right? The function phi. So what we do is that since we cannot afford to take a infinite number of points to get the accurate solution of the phi, we take a profile assumption of phi. For example, we can assume that the phi is we'll only take few points. For example, 1 2 3 4 6 7 8, like 9 points we'll take, and we'll make an assumption that between these points the value of phi will vary in some way. Maybe it may vary in a linear way. For example, there is a line between these 2 points, there is a line between these 2 points, there is a line between these 2 points. Okay, so what will we have is that we'll have an assumption, and this will lead us to a profile like this. We'll not get a very smooth profile, but we'll get a reasonable account of how things are, means how the fee is behaving. But if you see that since this is a linear assumption, there will be a lot of errors. For example, if say this is f and this is f prime, so there will be some error when we subtract this, right? But we can also take rather than a linear assumption, we can take a quadratic assumption. By quadratic assumption means the volume the function will require now 3 points, and it will be something like this. There will be a one function like this, there will be one function like this. Okay, and now the solution will be a bit more accurate, but not 100% accurate, because it is still an assumption that the profile of the function phi is varying either linearly or in a parabolic manner, quadratic way, sorry. So but here if you see this is f double prime, then the epsilon double prime, which is f minus f double prime, this will be far lower than f prime or epsilon prime, right? The two errors. So this is one way that we can improve the quality of our solution. By the quality of our solution, I mean how close your numerical solution is to the actual solution of phi, right? So now let us take a linear assumption. Okay, for example, this is uh, this is the p, this is e, sorry, this will be w, this is e. Okay, and we assume that the function phi varies between point w and point p, like a straight line. Okay, and also from point P to point T, it again varies varies linearly. That is, it will vary like a straight line. Okay. So now when we need the value of the gradient at the boundaries, we can simply, for example, this is phi w, this is phi p, and this is phi e, right? So now if you want the gradient, we can simply and we can simply find it. This is del x w, this is del x e. Okay, let this be the distance between points p and w and p and e respectively. Now so using this linear profile assumption, we can approximate this derivative, this gradient derivative of at this boundary E as nothing but phi E minus phi P minus of xe minus xp. which is nothing but all right. And similarly, for the west face, okay. Okay, now let's assemble the things. So the first part will be gamma E Ce minus Pp by delta Xe minus gamma W Pp minus Pw divided by. So mind this is small w, right? This is capital W del x small w plus Sp delta x equal to 0. All right. And these terms, the term phi E and phi W can be capital E, capital P, and capital W, right? You can find from these three terms. Okay. So now let's go ahead and rearrange this equation. So if we rearrange this equation, we will get to a useful form that we will use throughout the course, no matter what the equation is, ranging from the simple steady 1D heat diffusion to convection diffusion, unsteady problems, as well as for the Navier-Stokes equation finally. Hi, Monarch, can you just, if you don't have any questions, can you mute yourself, or do you have any questions? Okay, okay, fine. Thank you. Okay, so let's do the simple manipulations. So we'll take the phi p term to one side, say to the right hand side. Phi p, this is gamma E by delta Hc minus, okay. Yeah, this is also negative, so it will become positive when we come to the right side. W. Okay, we are done with these two terms. Now, what will be the phi? The phi E will have only gamma E by delta Xe. Okay. So now we have got a algebraic form, right? So this is the algebraic form. The 1D steady diffusion equation. Okay. Now what we can do is that we can we can name this term as AP, this term as AE, and this will become AW, right? And so finally, what does our equation become? It becomes AP phi P is equal to AE, right? Now, what is AP? AP is nothing but a summation of the AE and AW, right? This is nothing but the AE and AW. Okay. So what does it lead us to? So it leads us to a form of called a system of linear equations, right? So if you have a problem like this, a heat conduction problem T naught TL, and we divide this domain of our interest into, say, for example, 0, 1, 2, 3, 4, 5. So 6 cells, and we'll have phi naught, phi 1, phi 2, phi 3, phi 4, and phi 5. We'll have an equation for all these phis, right? So we have equation for phi naught, phi 1, phi 2, phi 3, phi 6, right? And this will be function of all the other phis. We'll see it may be the neighboring two phis, or maybe other. So so now we reach a system of linear equations. Okay, so this will be of a form like a matrix A times a vector phi is equal to B. Okay, and we have to solve this, and we solve this system of equation, often called as Ax equal to B, to get the value of x. Okay, so there are different methods to reach at the uh, to reach the solution. It is called, the first method is the direct method. So you must have studied in linear algebra that we can get the solution of x just by inverting a matrix, right? And you must remember how what a pain you had to go through to find the inverse of a 3 by 3 matrix, right? So if a matrix is 3 by 3, 3 cross 3, you had to first take the make the transpose and take the adjoint of A, then take the what all had to do, you have to take the determinant of A and all that to finally get reach at the A inverse. Okay, and in the inverse operation, we generally do all our CFD calculations in a computer. So what we have seen through many experiments and studies, that there is a cost required to invert a matrix is very high. It's very high, right? So if you have a matrix of 100 by 100, n cross n cross n, or maybe if you have a system, say you have a system, let me just, you have a system with n grid points. So n grid points you have, and you will then make a matrix which is n cross n. And to invert this matrix, you will need to make n cube operations. Okay, n cube different addition, subtraction, multiplication, this kind of operations you have to make. So just imagine if you have, for example, 10 cells, it will be nothing but 1000 operations. And if you go to just 100 cells, it will become how much? Around a million, right? Like 10 lakh, 1000, yeah, like 10 lakh operations. So from just increasing 10 times, you are increasing these things into 1000 times, right? So it is very, very, very costly to get the inverse of a matrix. So what general people do is they try something called the iterative method. So two very popular are the Jacobi and the Gauss-Seidel method. Okay, these are the two very popular methods. Okay, so till now, anybody have any doubt? Please feel free to ask me. Okay. Okay. Now we'll go through briefly how this Gauss-Seidel and the Jacobi method works. Just okay. Okay. So for example, we have say four grid points. Okay. E naught. Okay. And if we say this is phi A, which is nothing but a boundary value, boundary condition, and phi B. So this phi naught will be a function of phi A and phi 1, right? We saw that any point P for a linear profile assumption will only depend on its left and neighbors, right? But for phi naught, we only have a one neighbor, and this is nothing but a boundary value already known to us. So, so the phi naught will be some alpha phi 1 plus beta. We were say we'll write it as alpha 1 beta 1 or alpha naught beta naught. Alpha I and beta I are known constants. These might not be constant. We'll see later. And say phi 1 is nothing but alpha 1 phi naught plus gamma 1 phi 2 plus beta 1, right? Because the phi 1 has these two neighbors, phi naught and phi 2. Similarly, the phi 2 will have two neighbors, phi 1 and phi 3. So phi 2 will be something like alpha 2 phi 1 plus gamma 2 phi 3 plus beta 2, right? And similarly, for the last cell, for example, only one cell is left. So here also phi 3 will be something function of only phi 2 because phi v is known. So now we see that we reach at a coupled set of algebraic equations, right? We have reached at a coupled set of algebraic equations. Now, what does Jacobi say is that we will first guess the value of all the phis. Okay, say phi i's. Okay, and then using them, we solve for new phi i's. Okay, so for example, let's just take every value to be 1 or something like that. Then we'll solve this equation, right? Because phi naught will be nothing but alpha naught times 1 plus beta naught, and these are constants we know, so we get the phi naught value. Now phi 1 will be some alpha 1 times 1 plus gamma 1 times 1 plus beta 1. These are all known. We'll get the phi 2 value like that. So once we have done that, we'll have a new set of phi i's, right? So again we'll do new values, solve the algebraic equations, then we'll get another set of new values. So when do we stop, right? So this will be a never-ending process that will go on using the same using the previous step values of phi, and we do the next step. So we have to check whether the value has converged or not. Okay. Check for convergence. Okay, so how will you check for convergence? For example, there is a problem where there is a rod, there is a wall at 300 degrees Celsius, there is another wall at say 600 degrees Celsius or 600 Kelvin, 300 Kelvin, and you want to get the temperature of interior points, right? So T naught, T1, all these things. So how accurate you want it to be, right? So for example, you are designing a very critical mission critical part which needs to be very high tolerance, right? So you guys, if you have done mechanical engineering, you will understand the tolerance part, right? So all the temperature should be between say plus minus 0.1 Kelvin. Okay, so you will set some tolerance value, say epsilon 0.1 Kelvin. Okay, so how will you check for convergence? You will see, so for example at say um, at step 3 or at at a step n, you have values of Ti at say step n, right? And at step n plus 1, you have all the Ti's at step n plus 1. Then you will take the absolute value of Tin plus 1 minus Tin and check if it is greater than equal to the epsilon value, right? So so how will the temperature profile look like in the problem that the toy problem that I said? Say it is 300 Kelvin, it is 600 Kelvin. So this will be something like this, like right, a linear curve. And for example, at say step n, you have the value say 365.21, okay, and then you have at step n plus 1 you have the values 365.41, right? So then you will take the you will see the difference between them. You will see it is 0.2, right, and it is greater than the epsilon. So you will not stop there. So you will go to the next step, n plus 2, and you see it is coming as 365.42, okay, and then you will take the difference between them. It will come out to be 0.01, right, which is less than epsilon. Then you will know that this is where I stop my iterations. Okay, so it depends on your problem, right? So for example, if you want a very highly accurate solution, and if you give say epsilon is equal to 0.0001, then it will take longer, right? It will take longer to converge. So say it converges at n is equal to 100 steps, right? So if you take epsilon as 0.01, it will converge at n equal to 10. So it depends on your problem. So for the particular problem that you choose, if you whatever epsilon value you need, you define it that way, and then you will have to do a certain amount of iterations to finally get to the solution, right? So this is how all the iterative methods really work. Now I have shown you the Jacobi method. So what about Gauss-Seidel, right? So the main difference between the Jacobi and the Gauss-Seidel is at every step we use the updated value of the somebody. Okay. Yes, LU decomposition also we can do. Uh, so there is a method called TDMA, called tridiagonalization method, that is generally used. But in this course we will not be using any solvers, for example NCs or OpenFOAM. I can talk to the course instructor if it is possible, then I can give you a so I am not very much aware of how NCS works, but OpenFOAM I have worked on OpenFOAM, so I can give you a brief tutorial on how to build your cases. If many other people are interested, then we can do, but only for one person, then it will be futile. So I will do one thing. You everyone so if you have a group, then you can post about whether you will like a tutorial on OpenFOAM or some other solvers. But in this course I will encourage you to use some simple code for solving the diffusion equation or diffusion convection equation in Python or C++. I can also give you a brief code demonstration of how these are done. But now we will stick to the theory part, because this is how the course has been designed. I think it will be difficult for people who are not aware of these advanced terms to follow up. Okay. I hope this answers your question. This step will use the updated values, right? Of the updated values of the. Okay. By that, what do I mean? So let's go to the next page. Okay. So, for example, these are the, so at the superscript I have written as 0. That means the initial guess, right? This is the initial guess, and we have seen that phi, say phi 1, sorry, at the after the first step we'll get this phi 1 value, which is nothing but say ae phi naught at 0. Okay, okay, let me just, okay, so we let me just draw the domain here. Say we have a domain, this is phi a, phi, phi 0, phi 1, phi 2, and this is phi b. Okay, so from the discretized equation and the algebraic form we can write it like this, right? Is equal to 1 by ap times a phi a plus a phi 1, and also a source term, right? So let me just write it as a constant b, and these will all this is for the first step, and these all values we do not know, right? These are all the guess values. So all the subscript with 0 will be the initial guess. So we solve this phi naught with the initial guess. Now comes phi 1, it will be 1 by ap, this is aw, the a west is phi naught, but here we have the phi naught at the first time step, right, or first iteration, so we'll use that. And ae is phi 2, this we don't know, this will be phi 2 0 plus b. Now again phi 2 at 1 will be ap times aw, phi 1 of 1 ae will be phi b. Oh, this will be constant because the boundary condition. Okay, so what do we see? We see that in the Gauss-Seidel method we use the updated values instantly, right? Where whenever we get the updated values we use it. But in Jacobi method we will not do that. And okay, I think. Okay, I hope you got my point. So the point was that in Jacobi method, uh, when we are going through one iteration, it is called of a sweep. So when we go through a one sweep, we will only use the values from the initial guess. We will not use the updated values in Jacobi. Do not use values, but in Gauss Seidel we use the new values when we get them, right? So what changes do we see because of this kind of usage? We see that the Jacobi method is much slower to converge compared to the Gauss-Seidel method. This is very intuitive, and it is quite easy to understand why we get a much more faster solution. That is because we always use whatever updated values that we have in Gauss Seidel, but in the Jacobi we have to wait for the whole sweep to get completed so that we can use the new updated values. Okay, so these are generally slow, so we use some techniques to use techniques to faster convergence. Okay, so one technique is successive over relaxation, and the second way is a multi-grid method. Okay, so these methods we will touch upon later when we go ahead in our course, but this is the basic idea of how we first. So what we have seen that how we first convert the PDE into algebraic equations, and in that we use some approximations, right? So what are those approximations? Those are some profile assumption of phi, and also uh, averaging source term, right? So when we'll do this in a better way, we will achieve a more accurate solution. Okay, then once we have arrived at the system of linear equations or algebraic equations, we employ a solver to solve the system of linear equations, right? So this is the basic uh, methodology of how you will solve your governing equations in a numerical way. All right. But solving these numerical equations, we will face different problems. For example, there are some properties of schemes and solving techniques which will influence your convergence, the accuracy, and the consistency. Okay. So let's see what is accuracy, right? So the accuracy comes from the fact that if you remember, I showed you like there will be different ways you can approximate this profile. This may be a linear profile assumption, or maybe a quadratic profile assumption, right? You can take many assumptions of the profile. So this will give you, say this is the exact solution. This will give you some error EL, epsilon L, epsilon Q, and we'll see that the epsilon Q will be far less than epsilon L, right? This is because higher order assumptions yield more accurate results, right? So as we take higher and higher order of assumptions of different free profiles, we'll see that it is what is called, it's the solution that we reach at is more accurate. Okay. Now looking at the consistency. So what does consistency mean? Consistency is nothing but the fact that for example in a problem we will have a spatial discretization, for example delta x, delta y and delta z, and also a temporal discretization, say delta t. So it says that when these values reach to 0, okay, so when these values reach to 0, it does not reach to 0 actually, but when it becomes very very small, the solution approaches the exact solution. Okay. So what does a consistent formulation mean? It means that when the algebraic equation that we have, when we get the algebraic equation, for example the thing we got something like this, mm, gamma e by delta x e plus gamma w by okay. So when these delta x terms becomes very small, so this equation will yield the exact solution. Okay. But it is means you can very nicely see that these things, when these things go to 0, our truncation error term will also grow to 0, right? So by truncation error, let me just give you a recap. So what do you mean by truncation error? It is nothing but the error arising from the approximate representation of the differential operator. Okay, or we can not say differential operator, approximate representation of the partial differential equation. Okay, so what does it actually mean physically, right? So we saw that using the linear profile assumption, the d phi dx at say at the boundary E, we had something like phi E minus phi P by delta x. Okay, this is nothing but an approximation, right? This will have a truncation error. So if you remember from the last tutorial, I explicitly told you what is a truncation error in terms of a finite difference formulation. But let's see what it comes out for the finite volume formulation. Okay. So the truncation error in this case, what it will be? Okay. So let us write. Uh, Let me just draw it here. So this is our region of interest, right? The E boundary. This is the E cell, this is the P cell. Okay. Now we'll expand the P value and the E value uh, about the E boundary. Okay. So now the phi E will be nothing but phi E plus dou phi by dou, sorry, it will not be dou, it will be del because only one independent variable. So d phi by dx at E times, say this is delta x and this is delta x by 2, so it will be delta x by 2 plus order of delta x square. These are the term that we club everything together and only write the order of the leading order term, right? And similarly, phi p will be p small e minus d phi by dx at e delta x by 2 plus order of delta x square, right? Now we put these two values here. What do we get? We get d phi dx at E, which is where it is nothing but approximation of 1 by delta x of phi E is this and this will get cancelled and this will just get added up and delta x will become delta x by 2 will become delta x, so it will be d phi by dx at E times delta x plus order of delta x square, right? And finally we can write it like this. This is a approximation and it is nothing but d phi of dx at E delta x. Okay, so this will get cancelled. And this delta x will get divided here. So this will be order of delta x only. The square term will get cancelled. Okay. So you see now the error term, that this is the truncation error term, right? So the truncation error is of the order delta x. Okay, and this definition seems to be consistent, right? Because when delta x will go to 0, the truncation error will also go to 0, and this d phi dx at e will slowly become equal to phi e minus phi p by delta x. Okay, but sometime what happens, for example, something called the Dufort Frankel scheme, there are some terms like delta x by delta t in the truncation error, right? But when delta x and delta t will both go to 0, this will not go to 0, right? This will be some constant. So this term will always linger. So no matter how small your delta x or delta t is, you will always get a solution which is far worse, or far worse than the solution that we get when we have a coarser delta t or delta x, right? So this type of scheme is what is called a inconsistent scheme. Okay. So is there any questions? Any doubt regarding what we discussed till now? Okay. So to better understand how this default Frankel scheme and how these things uh, means how the scheme becomes inconsistent, I'll give you a example of how this is how this is uh, this default Frankel scheme is becoming inconsistent, and the truncation error term leads to the inconsistency. Okay. A moment. Okay, just give me 5 minutes. Let's take a break, and we'll again meet after 5 minutes. Okay. Meanwhile, please go through whatever we have discussed, and if any doubt you are having, we'll discuss it after this 5 minutes break. Okay, now let's get back and let's see how Dufort Frankel gives us a inconsistent scheme. Okay, so let us solve the steady one-dimensional heat conduction equation. So which is nothing but dt by T small t equal to k times. Okay. Okay. So now uh, the t, there will be a term here and there will be a term here, right? So let's just let me draw the depiction. For example, here we have ti, ti minus 1, ti plus 1, and so on at time say n. Okay, this is at time t is equal to n. Now at t n plus 1 we will again have ti n plus 1, ti plus 1, n plus 1, ti minus 1, n plus 1, right? This is for the time t n plus 1. And in the past we will have ti n minus 1, ti plus 1, n minus 1, ti minus 1, n minus 1, right? Okay, so you get the thing. So here this I corresponds to the spatial location and this J tells us about the temporal location. Okay, so now we will discretize this ODE. No, this is not ODE, this will be a PDE. Let me just rewrite it. This will be in terms of partial differentials, not ordinary differentials. So dou t by dou small t equal to k times dou square t by dou x square, right? And this is assumed or approximated like this. Okay, let me just write it in the down part. And this, so this is approximate in this way, and this the diffusion term is approximated in this way: I plus 1 at time n plus ti minus 1 at time n minus of ti n plus 1 plus ti n minus 1 by delta x square, right? Now what will we do? We will do a very common thing that we have done all along. We will expand the terms about TIN. Okay, we'll do a expansion of this term. So what will TIN plus 1 look like? It will be TI at n plus dt dx, sorry, dt, it will not be d, it will be dou, because it is a PD, dou t by dou small t at I, um, at time n times delta t plus dou square t dou t square at I n delta t square by 2 plus order of delta t cube, right? And ti n minus 1 will be ti n minus dou t by dou small t at I at time n dou square t dou t square at I time n delta t square by 2 plus order of. Okay, now if we subtract these two part and divided it by 2 delta t, what we will have? If we subtract these two terms, uh, this one and this one will get cancelled, this one and this one will again get cancelled, and this will get added up. So ti n plus 1 minus ti n minus 1 by 2 delta t, this will become delta dou t by dou t at I at time n plus 2 delta t, and then we'll divide it by 2 delta t. So this will get cancelled, plus order of del t cube. This will again get divided by delta t, 2 delta t. So finally we'll have tin plus 1 minus tin minus 1 by 2 delta t is nothing but dou t by dou t at time n plus order of delta t square. Okay, this looks quite reasonable. Now we have this term also, right? So tin plus 1 plus tin minus 1, right? So if we add these two terms, what will we get? So if we add these two terms, we will get, now what is the difference? The difference is that these two terms will get cancelled, right? Because this is an addition, this will become 2 ti at n. This term will also remain. So ti n plus 1 n minus 1 will give us 2 ti at n. This will get cancelled, plus this will again get added up. So this will be dou square t dou t square at I time n, and only delta t square, because 2 it is half, it will become 1, and order of delta t cube. Okay, okay, it's reasonable. We can also write it as 2 ti n plus order of del t square. Okay, so we are done with this term also. Now let's see this term, how it comes up. So again, so ti plus 1 at n is nothing but ti at n plus dou t by dou x at I at n delta x plus order of delta x squared. Similarly, ti minus 1 at n minus of dou t by dou x at I n delta x plus order of delta x squared. Okay, so now we will just add these two terms. We will add, where is it? Yeah, we'll add these two terms, right? Okay, my bad. We will have to incorporate this order of delta x term also. So it will be dou square t dou x square at I n del x square by 2 plus order of delta x cube dou square t square at I delta x square by 2 plus order of delta x cube. Now if we add these two terms, so ti plus 1 at n plus ti minus 1 at n, this will become 2ti at n. This term will get cancelled. This term will also add up and only become dou square t dou x square at I at n delta x square. The two will get the half and half will become 1 plus order of delta x cube, right? Okay, now in the left hand side, if you remember, we got this term, right? So let's write it down. We'll use this one. So the left hand side is, sorry, dou t by dou small t plus order of delta t square. Delta t squared, and the RHS will be, it will be a sum of this one and this one divided by delta x square, right? So it will be k by delta x squared of 2 ti n plus dou square t dou x square delta x square plus order of delta x cube minus this term, right? And this is nothing but this one. So it will be 2 ti at n plus order of delta t squared. So we will not bother about the sign in the order, this order representation, okay? So this will get easily cancelled. So what we finally have is that k times dou square t delta x dou x square, this and this term will get cancelled. Let's multiply it with this term. So delta x square and delta x cube, so it will become only order of delta x, right? And this part will become order of delta t square divided by delta x square. Okay, so if you look at the final equation now, our PD look like this, right? Dou t by dou, sorry, by small t k times dou square t by dou x square, right? This was the PD. And what will be our approximation look like? Approximation will look like this: dou capital T by small t equal to k times dou square t by dou x square plus this order of delta t square plus order of delta x plus this one order of delta t square and delta x square. Okay, so we can see that we have reproduced this partial differential equation into this algebraic form, but along with some errors, right? So these are the truncation error. And what does a consistent scheme look like? It says that when delta t or delta x will go to 0, the approximate solution will reach the exact solution, right? So if delta t and delta x goes to 0, we can clearly see that this term, this order of delta t square term will go to 0, this order of delta x term will go to 0, but this term will not go to 0, right? This term will only go to 0 if delta t term goes to 0. But if delta t and delta x term both goes to 0, these things will become a constant and it will stay constant, right? So no matter how fine your grid resolution is or how fine your time stepping is, it does not matter. The truncation error will always be some constant value, right? So we have seen the nature of the truncation error leads to an consistent scheme. Okay, so what have we seen till now? That accuracy and consistency arises from the scheme we have chosen, right? And the truncation error. So the accuracy of a solution will be say order of delta x or order of delta x square depending on the truncation error. And similarly, the consistency of a scheme will depend on truncation error. For example, if you have some odd looking or truncation error leading order terms, for example delta t square by delta x or something like that, these things will render the scheme inconsistent. Okay, so we have gone through the different uh, the nature of the numerical approximations that we have done. This will render a numerical solution either accurate or inaccurate or consistent or inconsistent, right? So this is the basic demonstration. So any questions till now about the consistency and accuracy? Okay, I think no questions now. So now we will look at another property called the convergence. Okay. So convergence is a property of a numerical method that arises from the solution technique, right? So by convergence we mean that whether the solution whether the errors that we have in the due to the approximation dies down as we go ahead in the as we move progress ahead in time, or does it remain constant, or does it grow? It depends on that, right? So this the convergence criteria is governed by something called the Scarborough criteria. Okay, I think sir has already given a brief introduction of what Scarborough criteria is. Just a moment. Okay, yeah. So there is something called the Scarborough criteria. What does it say? It says that the sum of all the neighboring coefficients divided by the coefficient coefficient of the particular cell should always be less than 1 at less than or equal to 1 at every cell, and for at least one cell. Okay, and always remember that this is a sufficient condition, and it also means that a it might not be accurate, right? So it only says that if this criteria is being satisfied, then your solution method will converge, but it does not mean that it will have a correct or accurate result, right? So we got a form something like ax is equal to b form, right? Which is nothing but a matrix of phi bn, right? And with the linear approximation, what we saw is that we for every point in the computational domain, we arrive at a form like this. Right? So we see that phi p only depends on phi e and phi w. For example, if we take the term phi 1, so this will correspond to the second row. This will only depend on these two values, right? So what we can see is that if we populate this whole row, we will see it will comprise of AP. Just a minute. It will comprise of minus of AE, AP, AW, and rest of everything will be 0, right? So this whole row will only have these 3 entries. Okay, and this AP term will be in the diagonal. Okay, so what does it mean? It means that if we do a summation of AE plus AW, this should be always less than 1 for every cell, and this AE plus AW by AP should be 1 for at least one cell, right? So these things will be achieved using the boundary values, right? These we will achieve using boundary values. I will show you in a small toy problem. Okay, so we have established the criterion for convergence. So if this Scarborough criteria is satisfied, then we will be left with a matrix which is diagonally dominant, right? So this matrix is diagonally dominant. By that we mean the magnitude of all the other elements which are not in the diagonals, the sum of all the magnitude of these entries should be always less than or equal to the AP. Alright? Okay. So now let us just look at one example problem. Let's look at a mm, let's say we'll do a 1D convection array conduction heat conduction equation, right? All right, now say the Q is constant, say 1000 kilowatt per meter cube, and we'll have two boundaries, so TA and we have the domain size L equal to say 2 centimeter, or let's make it simple, let's make it a 1 meter. K is 0.5 watt per meter per Kelvin. All right, let's divide it into 5 cells. Okay, So this is cell number 1, cell number 2, 3, 4 and 5. This is TA and this is TB. Okay. Now for the interior points, for like these points, it's very simple. So it will be, let's derive it. So T2, say A2 equal to A1 T1 plus A3 T3 plus Q. All right. And from the previous expressions, we can see that A1 and A2 and A3 say uniform mesh, that is all the spacings between them is same, so delta x and delta x. So A1, A2 and A3 will be nothing but k divided by delta x, right? From the general scalar transport equation, we saw that gamma by delta x, we got something like this. This is nothing but the same thing, right? A1, A2, A3 will be this, and also A1, A2, A3, A4 and A5. Everything will be this, okay? So these all values are same. And A2, A3, A4, okay, I think I have done a mistake here. This, let's write AP2, AP3, AP4, okay? And AP2 will be nothing but A1 plus A3, AP3 will be A2 plus A4, and AP4 will be A3 plus A5, okay? So now you have seen that the AP values, that is the diagonal elements, will be always equal to the sum of the neighboring coefficients, right? So now we have one criteria that we had, that is satisfied, that is at the interior cells. Now at the boundary points, so for example this is TA, this is say T1, sorry T2, this is T1, right? So the equation will T1 will something look like AT. So we have K times, for the east face it will be T2 minus T1 by delta x minus T1 minus TA by delta x by 2, right? Because this distance is delta x by 2 plus q times 0, and it will be T1 will be k by delta x plus 2k by delta x equal to T2 times k by delta x plus TA k 2k by delta x plus q, right? So in this term, so if you look at the matrix form T2, T3 and so on, this is for the T1, this is for the T1 grid point. The B takes care of all the constant, that is this part, so it will be TA2 TAK by delta x plus q. And what will be the coefficients here? It will be this one, which is AP, and only this east cell coefficient AE, right? And what is AP here? AP is AE plus some extra term, right? And all of this is positive, so this will always be greater than AE. And what are the summation of all the neighboring points? It is nothing but AE only, right? Only AE. There is no other neighboring points, right? So only, and everything will be 0. So only AE. So here we have that summation of A and B divided by AP is less than 1. So now we have these two conditions, right? So for the interior points, we have or we can write like this is 1, and for boundary points this will be same for the right side boundary also. Okay, this is less than 1. So now we have seen that we are able to satisfy both the conditions, right? So this, it tells us will converge, right? So this was a demonstration of how you can check whether the solution that you are expecting will converge or not using the Scarborough criteria. Okay. Now anybody has any doubts? It is already time. So I don't think we'll have time for doing a problem in this tutorial. But in the next tutorial, I will do a simple one-dimensional steady heat transfer problem and get the solution. We'll get the analytical solution also, and we'll get the numerical solution also. And with that, we can also compare how how accurate our solution is. So if no questions, then I will like to end this tutorial session now. Thank you everyone, and I'll see you in the next tutorial. Thank you everybody, and good night. Thank you, Deepraj. Good night.